Hi there and welcome to this video for Senior Physics on Electrostatics and Electricity. In this video we're going to continue our exploration of resistance and we're going to look at internal resistance. Now internal resistance basically talks about the type of complex chemical reactions which occur inside the battery, and it's a resistance which opposes the flow of current just like any normal resistor would do. Now we can't actually measure the internal resistance, but by using data which we collect from using current and voltage from a circuit, we can actually calculate what the internal resistance is. Now if we look at a battery, and you know that batteries decrease with the amount of energy they've got with time, and eventually they go dead. Now this is down to the chemical changing and breaking down within the battery itself, and as a result you can't put on enough electrons on one end to make it negatively charged to produce a potential difference. Now if we took a 1.5 volt battery and we put a copper wire to both terminals, we would expect to see a huge amount of current flowing. Why? Well, basically there's no resistance within the wire, so we would expect all of the charge to flow from one end to the other as quickly as possible. Now this can be shown using a very simple equation. So if we give the wire, for example, a very, very low resistance of, let's say, 0.01 ohms, then we would expect a current of approximately 1500 amps to be generated. Now 1500 amps is 1500 coulombs of charge flowing per second. And that's been calculated by rearranging the V equals IR equation that we looked at in our previous video. Now obviously, if you've ever taken a AA battery, a 1.5 volt battery, and put a wire to it, if you had 15 amps running through that, you would basically expect to get a lot of heat being generated because of the friction of the electrons moving through the atoms. Now this clearly doesn't happen. I mean, you can put your tongue on the end of the terminal, and you don't get a massive electric shock. Now why is that? Well, basically there's something happening within the terminals which is preventing the flow of current going from negative to positive. Something's slowing it down. Now this is down to the internal resistance. Now the internal resistance is basically the battery opposing the flow of current. Now when we draw this in a circuit, we tend to put, we have the battery, and we tend to put a resistor alongside it, and then we put the whole thing in the dotted line. And basically what it's trying to look at is the resistance within the battery is acting with the electromotive force or the push of the chemical itself. Now the thing is, what we've got inside the battery is a variable resistor, because what we tend to get is the push from the battery, from the chemical reaction, is going to decrease with time, which means that the internal resistance is actually going to act up in the opposite direction. I'll talk more about that in a second. So here we've got a diagram showing the internal resistance that you might get in a question, or it's how it's represented in the textbook. Now what you've got here is the battery, which can be seen by our normal battery symbol on the right hand side, and it's given a symbol epsilon. Now that epsilon basically talks about the electromotive force. This is the force necessary to push the electrons to one end of the battery, the negative terminal. Now the resistor part will act in the opposite direction. Now when a battery is acting at full capacity, we will get out, let's say a AA battery, you'll get out 1.5 volts of energy. If we put a voltmeter across that, V, we would get 1.5 volts, which would be a potential difference of 1.5 joules for every coulomb. Now, as the battery gets older, what happens is the chemical breaks down. It has less of a push. It's still trying to push with a force of 1.5. As the chemical breaks down, there is backflow of the electrons to the positive terminal. So they're going in the opposite direction, which means we generate a small current, which is actually occurring inside the battery. Now, if we work on natural current flow going from negative to positive, the electrons, as we flow negative to positive from the terminals through a wire, the electrons inside the battery begin to move across from negative to positive and change the flow of current. They oppose it, and as a result, it's like having your own little resistor placed inside the actual circuit itself. Now we can calculate the internal resistance using this algorithm here, where the output or terminal voltage V equals the electromotive force. This is basically the force that the chemical is trying to push the electrons to the negative end of the battery, minus IR. Now IR is the current flowing in the battery, as well and as a result the resistance that it generates. Now what you notice there is you get this negative value. Now the negative basically means it's acting in the opposite direction. So although we're pushing energy to one end, some of it is flowing back in the opposite direction. We've got this vector notation, which means that the overall potential difference between the negative and the positive terminal of the battery is going to decrease because we're going to take it away. Now, a battery will act at its best output voltage when there is no current flowing through the battery itself from negative to positive. The electromotive force generated by the chemical is enough to push all the electrons to the negative terminal, and there's no dripping back of the electrons to the positive terminal. As a result, your output voltage will be 1.5 joules. However, in half, if it's going to go through half its life, then the chemical doesn't have enough to actually push all of those electrons, so some drip back. When it's dead, what we notice that for every electron which is pushed to another side, another electron will move back. It's almost like having people trying to push a group of people down one end of a room. If you've got lots and lots of people, i.e. the chemical, then the result is none of the people can get to the other side of the room because we can push it there. Now they can all push with the same force, but as the chemical starts breaking down with time, you lose some of those people. By losing some of the people that you're trying to push down one end of the room can actually drip back onto the opposite side. It's like trying to use your hands to plug all of the holes. You simply can't do it. So that's what happens with the resistance inside the battery. So as I've stated, internal resistance will vary with the age of the battery. Generally they're around about 1 ohm. Now let's have a look at a simple example here, and doing the examples hopefully will help. So here we've got a student tested an old torch cell with a voltmeter. So it's a battery which is tested with a voltmeter. Now the terminal voltage is 1.5 volts. Now this basically means that there is an EMF in the current, in the chemical, which is pushing 1.5 joules per coulomb of energy down one end. So it's all trying to push. So these are our people. The chemical is our people trying to push a group down to one end. Now, assuming that the voltmeter draws a negligible current, so basically we're basically saying that there's no energy loss. But when it's connected to a lamp, the cell doesn't glow. So we've got 1.5 volts of energy trying to push the electrons down one end, but it doesn't glow. So something's happened. Now, when the cell is connected to the lamp, its terminal voltage, instead of being 1.5, when we measured the voltage across the negative and positive terminal, comes out at 0.5 volts, and it's delivering a current of 0.2 amps. That's the drip feed back from negative to positive. So we've got to calculate the internal resistance of the cell. So let's have a look at it. So we know the terminal voltage is given by V equals EMF minus the voltage across the resistor, the internal resistance. Now the EMF is the push that the chemical has inside the battery. Now we know that to be 1.5 volts. However, we've got a voltage across the internal resistance of the battery. Well, this is calculated by IR. Well, we know the current is delivering 0.2 amps, and we know that basically we've got 0.5 volts coming out of the actual battery. So what is causing that 1.5 volts EMF to be converted into 0.5 volts of energy. We've got to have lost some. So we can calculate R by substituting in. So we've got V equals epsilon minus I times R. We know that the V across the two terminals is 0.5 volts. We know that there's 1.5 joules of energy per coulomb trying to push the electrons down to the negative terminal, but we also know that we've got a backflow of 0.2 amps. So by rearranging the formula, we get 1.5 minus 0.5 volts divided by 0.2 amps, which gives us a resistance of 5 ohms. So basically what we're saying is, although we're trying to get it through a circuit, we've got a circuit of 0.2 amps, there is a backflow going back. Now if you think about it, the backflow, to get a continuous, because we're in series, is going to counteract it. So that's why we get that negative symbol which is utilized. Look, I hope it's that this has helped. It's quite a complicated area to deal with, but if you follow through with the actual algorithm and work your way through it, it sort of makes sense. We're losing energy from the battery due to the breakdown of the chemical, which means that as it gets older, we get more of a shove in the opposite direction, which opposes the normal current. Now, obviously, if the current is in series, it's going to slow it down, but the current across the whole circuit will be exactly the same. Okay, well, thank you for joining me, and I look forward to you joining me again when we'll look at series and parallel resistors. Okay, thanks for watching.